Could we settle down, please? So Jenny has reminded me that I should give you a reminder that there is this presentation today at 11:30, which means that I need to get out of the class, but you should stay here. It's mandatory. She's warned me that unless you go to this presentation, you won't get a job. So whether you take my class or not is unimportant, but you need to be here. The other thing before I start is any questions from last week? Anything that you want me to cover again? The few things that I heard from Ali was there was a confusion regarding simplex, that it wasn't covered enough. There was also a worry about sensitivity analysis, and I'll go over both of that today. Anything more? Anything else that you want me to talk about before I go on to the next material? Duality, yes. Duality is a bullet today. That's going to be covered in detail today. Yes, sensitivity analysis, which includes shadow prices, which includes something called reduced costs that we didn't talk about in last week. Anything else?
What is a primal?
What is a primal? That which is not a dual. The initial LP that you start with is primal. And that which you get from taking this duality is the dual. So if you started with the dual, that becomes the primal and the other becomes the dual. Okay, so let me talk about simplex first, and then I'll talk about duality, and after talking about duality, we'll go to sensitivity analysis. So the story of simplex is that, as far as I'm concerned in this class, all you need to know about simplex is the fact that everybody has made sure that they've read this notice, so I can erase it. Okay, so the main thing that I want you to remember from simplex is that it works with the standard form LP. So I don't want you to know how it works essentially, but these are the things that I need you to know. I need you to know what a standard form LP is. And a standard form LP looks like you're either minimizing or maximizing some function C transpose X such that only equality constraints and X greater than equal to 0. The next thing I want you to know is that at any solution that simplex produces, if there are m equations here and n variables, then at any solution that simplex produces, at most m, so this is the same as the number of equations, variables are positive. The other thing, here are the two things that you need to know further more than this, which is that these m variables, the positive variables, are called basic, and the zero variables are called non-basic. The next spot is that simplex moves, and I bet that is not visible to anybody, so let me move this up. Simplex goes from corner to corner by moving in non-basic directions. Some variable that is 0 at a particular point, it will try to make it non-zero and move to a new corner. What does it mean? So you need to be able to answer questions of the following kind. Suppose I give you this problem. Maximize, this is our beer problem, we'll come to it in a moment again. Um, what was it? No, 4. And each of the x's are non-negative. And suppose you gave simplex this problem to solve, which is you put it into a solver and you asked it to solve it, and it produced this answer. X is equal to 10, 26, and say 3. Is this possible? Does everybody see why this cannot be an optimum solution produced by simplex? So the basic idea is that what I want you to know is to have a sanity check. Typically, when you get any solver to solve it, it gives you an answer. Sometimes it's always good to have an idea of what should that answer look like for you to be able to go back and check whether this makes sense. So this cannot be an optimum solution that simplex could return. What about this? Could this be an optimum solution? And I'll give you another. Could this be an optimum solution? Yes. So the thing is that it needs to be at most m variables. It could be less than m variables. And the reason, so in order to conclude this, one has to go through several steps. First, this is not a standard form LP because it's got inequality constraints. So what you do is you first put it into standard form. When you try to give it to solver to solve it, you don't care about it. But when you want to make some statements, you want to convert it into standard form. Don't care about it. So now there are 5 variables, 2 equations. So at most 2 variables can be positive, which means that this cannot be something that simplex could return. If simplex returned this, there is some error, which means that either you did not formulate the problem correctly or something else happened. One likely would be that somewhere in your spreadsheet something is there which allows a third constraint to be present, which would make this a possible solution. This can be a solution because what this says is that there is at most 2 variables would be positive, but it's possible that some of the slacks are positive, which would return this as the optimum solution. So that basically covers this story, and that story.
There's also some relation between m and n, and also infeasibility, in the sense that if m is less than n.
So if m has to be less than n, if m is greater than n, then this problem has a unique solution. There is no optimization left. Yes?
If there are exactly m variables that are positive, like if all m variables are positive, does that mean all the constraints, the constraints are
right?
Yeah.
No, not necessarily, because what could happen is x1 could be positive and s2 could be positive.
Okay.
Right? So there are 2 ways of looking at it. In this problem, all constraints, these equalities are always tight. So in the standard form LP, there are equations. They're always tight. When you convert something into a standard form LP, then it is possible that there are slack constraints. And what that basically means is some of the slack variables are positive.
Well, then if the x1, if the variables that you care about, the non-slack variables, if they're all positive, if they're all on the basis, then they're all tight, right?
Yes.
Okay.
Yes. If all the variables, if really what this solution should have been looked at was maybe 0 and whatever is the slack, 25 or something. If these are the ones that are positive, 2 of these are positive, it means the 2 constraints are tight. Okay? This part we haven't done yet, and this part gets related to something called reduced cost. And let me go to duality right now, and then I'll return back and talk about this last bit that you need to know about simplex. All right? Okay. So today what we'll start with is that if you're given a general linear program, and let me put down an example here that I'm going to use. It's down here, and then we'll go back to those rules and construct it. you can use the one that's there in the notes. I'll write it out again here. So this last bit that we haven't covered, we'll come to it once I'm done with duality. So here is the primal program that I'm going to start with. I want to maximize 3x1 plus or minus 2x2 plus x3 such that 2x1 plus 4x2 plus 5x3 is less than or equal to 4, x2 plus 7x3 is equal to 1, x1 is greater than or equal to 0, x2 is less than or equal to 0, and x3 is free. Okay, and what we want to figure out is how do I construct the duals. So let's go back to the general thing and we'll use those rules in this one. So a general LP would look something like this. You will have a bunch of constraints which look like less than or equal to type constraint. So that's a less than or equal to type constraint. You'll have a bunch of constraints that would look like an equal to type constraint, which is here. And in this LP, there is no greater than or equal to type constraint, which is this one. Now, there is a difference between these kinds of constraints and the one down here. They also are, you could pretend that this is a constraint which looks like this one, and that's a constraint which looks like that one. But the special thing about these constraints is that they involve only one variable. So typically when you take duals, you separate the constraints into two sets of constraints. One set of constraints which we'll call a main constraint. That's a main constraint because that involves multiple variables. These guys down here, which involve one variable at a time, will be called variable type constraints. All right? So main constraints have more than one variable, and variable type constraints are something, and this notation here would mean that I don't know what happens here. There is some sign. It's either greater than 0, less than 0, or free. So when you construct the dual, for every main constraint, you need to introduce a variable. Every constraint in the primal, so there was a question, what is a primal? This is what I start with, therefore this is primal. And now I'm going to construct a new LP that will have a relationship to this LP, and therefore I'll call that the dual LP. So I'm going to put a variable for each of the constraints. So there will be a variable type constraints for this one, which will say U1 something, I don't know yet what it's going to do. Here's U2 something, I don't know what I'm going to do that. Then for every variable constraint, you will go into, for every primal variable constraint, you'll introduce a dual main constraint. Right? So here, this is a primal main constraint. Corresponding to that, I've put a dual variable constraint. This is a primal variable constraint. I need to put a dual main constraint for that. And what do? I look at this variable. I look at all the coefficients that multiply this variable. What are the coefficients? I'm just going to expand this to 0 times x1. So you've got 3, which is the objective coefficient. That will come onto the right-hand side of this. So 3 will sit here because I'm talking about x1. On the left-hand side, again, I don't know what the signs are going to be here. What I'm going to do is I'm going to multiply u1 times the coefficient here plus u2 times the coefficient here. So it's going to be 2 times u1 plus 0 times u2. And I still don't know what's happening here right now. The same rule happens to the next one. And just to expand this, I'll put 1 times here. Corresponding to this, I look at its coefficient here, which is minus 2, put it on this side. And on the left-hand side, I'll multiply its column. That's what this capital A stands for. It's the column of the A matrix. So I'm taking the column and multiplying it to the variables component by component and adding them up. So it becomes 4 times u1 plus 1 times u2. Again, I don't know what's happening here. I'll correct that in a moment. All right? So far, so good?
Excuse me, sir.
Yes.
Only for the variable constraints.
Yes.
Can you explain how you got the equations?
There's no equation right now.
Another equation, the 2u plus 3u.
This one?
Yeah.
Okay. So what I do is I'm putting a main constraints corresponding to variable x1. So I take the coefficient in the objective vector, which is 3, and put it on the right-hand side. Then I look at the column corresponding to this in the constraint matrix here. What is the column? 2 and 0. I multiply that to the variables u1 and u2, add them up and put them here. So 2 times u1 plus 0 times u2, something 3. Similarly over here it's 4 times u1 plus 1 times u2, don't know yet what comes in here, minus 2. And do the same thing with the last one. It becomes 5 times u1 plus 7 times u2, something 1. Now what happens to the objective? If this is a maximization problem, this becomes a minimization problem. Whatever was the right-hand side vector here becomes the objective vector there. 4 times u1 plus 1 times u2. Right? Yes?
Would this just translate to 3 variable constraints for the primal in the sense that x3 is free? Wouldn't you translate it into 2 separate constraints?
You could do it if you wanted to, but so the reason we like to do it this way is that if you were doing it by simplex, yes, you would have to make it into non-negative variables. But most of the solvers nowadays would take x3 free as a variable in there.
Because this was supposed to act like a check on the number of variable constraints, right? In the dual.
Which one? No. If you have a question, ask here, so that everybody could benefit from your question. So the LP by itself can be formulated any which way, right? If I want to solve it by simplex, I need to convert it into a particular form. So when I look at duality, I don't want to restrain myself to what simplex wants. This is the most general primal that I could think of. I'm going to construct its dual. At the moment, I don't really care where this came from. Somebody gave me this thing, and now I'm looking at what happens to the dual. That's about it. Okay? Any other questions at this point? CVN has a question. Hello? Sure. Okay. So now all that remains is how do I fill up these blank spaces? Question. New objective function. So the primal right-hand side vector becomes the dual objective vector. So the primal right-hand side vector here is 4 and 1. That comes up and sits up there. So it becomes 4 times u1 plus 1 times u2. And if you go the other way, the right-hand side vector is 3 minus 2 and 1. That becomes the objective vector there. A max becomes a min. Okay? All right. Now we want to fill up what happens here. And this is something that I can never seem to understand and remember. I could create it for you, but this graduate student of mine gave this rule called the sensible odd bizarre rule. And that allows you to set up what happens to the signs here. And what this rule says is, first let's look at a minimization problem. Okay? Now, we are looking at a primal which is a maximization problem. Let's start looking at the maximization problem. Typically, what happens in the maximization problem is that you're trying to maximize something, you're trying to increase variables. So the sensible constraints would be one that limit you from the top. So any constraint which is less than equal to type will be a sensible constraint. So this guy over here is a sensible constraint. It's a maximization problem and it's a less than equal to type constraint. Equal to type constraint would be called an odd constraint. So this will be an odd constraint. So those are these, when I say min and max here, what I meant is look at the main constraint of a max problem, categorize anything which is less than equal to type as sensible, categorize anything which is an equal to type as odd, and if you have got a max problem and if you've got a constraint which pushes the variables up, then you call that a bizarre constraint.
So there is no bizarre.
There is no bizarre constraint here. Okay? Question? Yes?
Isn't x1 a bizarre constraint?
Hold on. This is just for the main constraints. So the question here was that isn't this a bizarre constraint, x1 greater than or equal to 0? Well, there is some artificial separating out. So these statements are only valid for the main constraints, not for variable constraints. Here's what is variable for the variable constraint. Greater than or equal to variables are sensible. So this is a sensible variable. that, by this rule, is a bizarre variable. A variable that is less than or equal to 0, I'll call a bizarre variable. So this is bizarre, and that's odd. x3 equal to free is an odd variable. Okay? Now what you do is that you take these and transfer over onto the other side. Whatever labels that you put on this side, assign those labels on the dual. So this has to be sensible, that has to be odd, this has to be sensible, that has to be bizarre, and that has to be, actually, I flipped things. Did I put them right? Oh, okay, good. This is bizarre. So here you go bizarre, and that you copy here odd. And now you work backwards. Here you label the variables based on what the constraints and variables look like. Here you put in the sign constraint based on what labels you got. So if this variable has to be sensible, what kind of a constraint comes in here? Greater than equal to. So this becomes greater than equal to. If this guy has to be odd, what has to be its variable? Free. So this becomes free. And what about here? So it's a minimization problem, and you want the constraint to be sensible. So greater than equal to. So this becomes a greater than equal to constraint. This guy has to be bizarre. So this becomes less than equal to. And finally, this has to be odd. So this becomes equal to. Okay, it's not my computer dying. All right? Yes?
Which grad student gives you the SOB rule?
So my old notes used to say any acronym is all you're doing. That's why I put it as sensible, odd, bizarre rule. So I don't hold anytime you start shortening these rules, it's all up to you. Yes?
In order for this to work, you have to have the main constraints first, and then the single constraint second, or the variable constraint second, and the primal, and then have the variable constraints first, and the
Don't care. So, okay, the question here was, in order for this to work, do you have to put them in that order? No, you don't, because when we made decisions about this constraint, for example, we didn't care about where this constraint was there. If I put it down here, I would still have called it a sensible constraint. I didn't look at any of the things below it in order to decide whether this was a sensible constraint or not. The only thing I needed to know was whether this is a max problem or a min problem.
But to do the other side, to have it match up with that side, you
Right.
have to have it exactly.
So the reason I put it this way is because it just makes it easier to understand. Once you start getting used to taking duals, you don't have to write it this way. If you write it this way, it's very clear what's happening. For every main constraint, there is a variable constraint. For every variable constraint, there is a main constraint. And there is a relationship between these two. Okay? But once you get used to taking duals, you don't have to write it this way. You can write it in any which way you find it convenient. It just makes it easier for us to do it, put things in this manner so that we know what is going to happen and where what is going to fit in. Question?
The third constraint there has a 0 U2 on the dual side.
Yes.
Why do you consider that a main constraint? Because it's still going to be a variable.
Well, the only reason I consider a main constraint is because of the way it came out of the primal. If this was something that I would have started it, I could start off with this being a variable constraint. That's fine. The only reason I call that a variable, and that's why this differentiation between variable and main is sort of artificial. The only reason that we do it is that if you have a constraint which looks like this, which has got a 0 or free as the right-hand side, it's very convenient to take duals. So let's say that the definition of a variable type constraint would be, could we have the question directly here, please? Is that when you have right-hand sides, which the left-hand side involves just one variable, and the right-hand side either is 0 or free, then taking its dual is very easy. So I want to consider this as special ones because I don't have to put in a dual variable for this guy. I don't like too many variables, it just increases my optimization problem. Don't want variables, so I don't need variables for these. But if you want to go through the exercise of putting a variable for these two, you can eliminate them out. And so it's not going to make any difference at the end of the day. All right? Okay, so let's try one more, we'll add one more constraint to this just to get fixed ideas that we know what we are doing, and then we'll go on to looking at duality a little bit more. Okay, so suppose I add this constraint to this problem. 3x1 plus 2x2 plus 8x3 is greater than or equal to 2. Suppose I add that constraint, and let's make this all black. And I'm definitely not going to be able to reproduce what I wrote last time. So just use the old one, it doesn't really matter. Okay, suppose this, I add an extra constraint in the primal. What kind of changes will happen in the dual? You will have another variable. So you will introduce a new variable here. Let's call it u3. And we don't know what's going to happen to its sign for the moment. Let's not worry about it too much. What else is going to happen?
The three variables in the dual would change as well. The coefficients would appear on the other side, as in 3u3 in the first one, and then 8u3 in the second constraint, and 10u3 in the third one.
Right. So these constraints are going to change. Would the signs change? No. So you'll introduce a new variable, which means that you'll introduce a new column here, which will be plus 3u3 plus 8u3 plus 10u3. And since I've erased the signs, let's just make it an exercise into trying to figure out what the signs are again very quickly. What will be the sign here? It's a sensible constraint, and now the constraints have gone off the board, which is very convenient. Greater than or equal to. A bizarre constraint? Less than or equal to. And an odd constraint is an equal to constraint. Okay, so those are the changes. And what about this guy now? So what kind of a constraint is this? This is a bizarre constraint because it's a maximization problem and you're trying to push. Oh, sorry. Very good. You guys are better than I am at this. So this will be a sensible variable, and therefore the sign here would be greater than or equal to 0. All right? Question?
I have a question regarding this. Is the quality of the problem has changed? Maybe you want to first check is there a unique solution or not, because there's already 3 constraints.
Well, okay. So let's not worry about trying to solve these problems. Let's just look at qualitatively what is happening to the dual. At the present moment, I'm only worried about making sure you know how to construct the dual. Question?
If instead of 0, like if you had a constraint that said like x1 has to be greater than or equal to 3 or something like that,
Yes.
How does that change? Does it just change the 0 and the, I guess how does that change?
Okay. Question here: if x1 has to be greater than or equal to 3, how does taking the duals change? Instead of having 0 right hand side, what happens? 2 ways of doing it. One way I would say is that this is a very artificial variable. I'm going to define a new variable which is 3 plus x1. So then that becomes x1 is greater than or equal to 0. That's one solution. The other solution is not to treat it as a variable type constraint. We're going to treat it as a main constraint because there is the variable type constraint. Let me rephrase it. Should have been 2 things. Only one variable, and the right hand side is 0 or free. It's convenient to work with those. Inconvenient to have something on the right hand side. All right? Okay. So let's go back to removing, well, let's keep the constraint there. It doesn't matter.
So the objective function is also getting.
Yes. What happens to the objective function? You end up getting 7 times u3 sitting here. Good. All right. So why do we care about the duals? We care about the duals because the primal and the dual optimal solutions are equal. So first story, and we'll use that in a moment momentarily. First result is that the value of the primal, let's call this P for primal, and let's call this D for dual. So the value P is equal to D if either P or D is less than infinity. It's finite. Let's not say less than infinity. So something, it could be minus infinity, is finite. If either the primal solution, yes.
In the previous class, when we found out the dual
Yes.
from the primal
Yes.
using the upper bound, we actually found that P was less than or equal to D.
Yes. Yeah, P was less than or equal to D.
Yeah, so how does that, I mean, you're not saying that P is equal to D.
Which is a stronger result. So if you go back to what happened in the last class, if you look at the next chapter, the next whatever notes there, it has P equal to D, which is a strong duality. That is a proof that we didn't do in class.
Okay.
So there, it takes a little bit of, so let's start off. So this is always true. P is less than or equal to D always. No questions asked.
So, couldn't understand.
So the question here was that in last class we constructed the dual by looking at an upper bound for the primal. And no matter what I do with the dual, it is always the case that the value of the dual is greater than or equal to the value of the primal. However, if it turns out that either the primal or the dual is finite, then you can say a stronger statement. And the stronger statement that you can say is P is equal to D. So P is less than or equal to D does not eliminate that case. But if one of them is not, if these are not finite, then you cannot say that P is equal to D. Only in the case where the value of either the primal or the dual is finite, you can say P is equal to D. And we'll use this property probably on Thursday, where P and D are not finite. And we'll have to consider what happens there. So for now, let's not worry about that case. We'll re-examine the duals again when we need it. Right now, all I'm saying is that this is always true, and this is true if one of the values is finite. Yes?
So I can't understand the physical significance of the primal and the dual, and how can they be compared like this? I mean, I can understand that you can make a dual out of a primal.
Yes.
But what's the physical significance, and how can we compare the two, and how do these results follow? The ones that you written on the right hand side.
Okay. So there are several questions in there. So the question was, what is the physical significance of the primal and the dual? And how do these results follow? So this result, actually, we showed in last class. We showed that we can construct a dual, and for every feasible value in the dual, you get an upper bound for the primal. You take the minimum of that, you still get an upper bound. So one way of thinking about the duals is simply another linear program that one has constructed in order to get bounds on the primal. Primal is a maximization problem. Getting bounds is hard, upper bounds is hard, so I construct a dual which will give us an upper bound. Now, this becomes a very happy situation if it so happens that one of them is finite, then P is equal to D. Now, as regards the physical significance, bear with me for a moment, you'll get to it. Okay? So far, these are the two things I want you to remember. The third thing is something called complementary slackness. Suppose X star is the optimum solution of the primal. So it's a 3-vector, X star 1, X star 2, and X star 3. And when I'm saying that this is an optimum solution, I am already assuming that the primal has a finite optimum value, because otherwise there won't be an optimum solution. Okay, so I'm already assuming that it has a finite solution, and let U star, which again in this case has 3 variables, be the optimum dual value, dual solution. Why can I insist that there will exist one? Because of P is equal to D. If P is finite, D is finite, and there must exist an optimum solution. Then, these satisfy something called complementary slackness. What you do is you take the constraint and multiply it by its corresponding variable, then that, and what do I mean by saying multiplying a constraint with a variable? Here's what I do. I take 2x1, evaluate it at, so I evaluate the constraint at the optimum primal, and I take the left-hand side and move it to the right-hand side. So I just set it -4, multiply this by its variable u1 star, and that must be equal to 0. So complementary slackness says that you take the constraint take its corresponding variable, multiply them, and set that equal to 0. What does that mean? It means that suppose this constraint was slack at the optimum solution. Which means what? Which means that the left-hand side here is strictly less than 4. Which means that this bracket is not equal to 0. Then the corresponding dual variable must be 0. If the constraint is slack, then its corresponding dual cannot be positive. It has to be equal to 0. That's what this implies. Right? So this implies that this is slack. This implies that u1 star is equal to 0. We'll come to that. This is one of the things that we used last class. We were talking about the constraint with respect to coherent, and I said, well, if the coherent constraint is slack, then its corresponding dual variable should be 0, and we argued that by looking at change in the objective. Here, it's another theorem. It says that complementary slackness must hold, and it goes both ways. Here we took a primal constraint and multiplied it by a dual variable and set it equal to 0. The same thing happens the other way too. So we can take x2, multiply it by its dual constraint, which is 4 u1 star plus u2 star plus 8 u3 star minus 2, and that must also equal 0. Question?
So basically that's like saying S1 times U1 star is equal to 0 and S2 times U2 star is equal to 0.
Right.
Or X2.
So you could have reformulated this problem in terms of the slack variable, and the slack in this constraint is simply the difference between whichever, it depends on how you want to define the variable. So if you wanted to write it in terms of the slacks, I would have defined it as 4 minus 2x1 star minus 4x2 star minus 5x3 star times u1 star is equal to 0. Then it will be a slack interpretation.
So the purpose here is just to find out the value of the dual?
No, the purpose is to say here, so some of these things are just algebraic properties for now. When we come down to application, these algebraic properties would be interesting. So in optimization, typically what happens is that you have some application, you create a model, you solve that model. At this point, we are in the math mode. We don't really care what's happening here. It's some algebra, and I'm just manipulating that algebra. We'll come back to applications after we've understood what's happening here, and we'll apply it to results. Okay? All right. Question?
Could it be possible in the equal to 0 quadrant, both the bracket is equal to 0 and the u1 star is equal to 0?
Yes, it is. So only thing that complementary slackness tells me is that the product of these two terms must be 0. Therefore, if this is slack, it means that must be 0. If this is not slack, meaning this bracket is equal to 0, it doesn't give me any information about what happens to u1 star. It could be positive, it could be 0. I don't have any information. Now there is, for those of you who have seen linear programming before, there is this thing called the Goldman-Tucker theorem, which says that you can always find a primal solution and a dual solution such that if one is 0, then the other is positive. It's not necessary that this will happen at all solutions, but the Goldman-Tucker theorem says that yes, it is possible to find solutions which are strictly complementary. And that story that Goldman-Tucker theorem will come to help us when we talk about arbitrage. And there is a use for Goldman-Tucker there, but when I come to it, I'll probably not call it Goldman-Tucker. There is an easy proof, so might as well just talk about the proof rather than the theorem. Okay, so far what have we learned? We've learned that given a primal, I can construct a dual using the sensible odd bizarre rule. If the primal or the dual has a finite value, then they are equal. It's always the case that the dual is an upper bound on the primal, or vice versa. Primal is a lower bound on the dual. We know complementary slackness, and now we will start understanding what happens. Why do we care about duals? So far, it's all algebra. We're going to start using these definitions in a moment. So let's go back to that example that we had, and we'll talk about what does it mean. Towards the end of last class, we started looking at the use of duals, and let's return to that story. Here's the problem. We were trying to maximize, 13 times x1 plus 23 times x2 such that 5 times x1 plus 15 times x2 is less than or equal to 480, and 4 times x1 plus 4 times x2 is less than 160, x1 and x2 is greater than or equal to 0. And its dual is going to be minimize 480 times u1 plus 160 times u2 such that 5 times u1 plus 4 times u2 is greater than or equal to 13, 15 times u1 plus 4 times u2 is greater than or equal to 23, and u1, u2 greater than or equal to 0. Here again, so to answer one of the questions that was raised before, do I have to put things in that order? I don't. I know how to construct duals, or at least simple duals like this, I can do it. And therefore, I can write out the answer. Okay. So we'll use the first result there, that the value of these two duals, primal and dual, is equal. No matter what right-hand side I put here, as long as I put a finite right-hand side, the feasible region of this LP is finite. It cannot run off to infinity. Therefore, for all right-hand side vectors, the primal is finite, which means that the dual is finite, which means that their values are equal. That's rule number 1 there. Okay? Now, typically, the way we're going to use the duals is we're going to make this assumption. This assumption is called the non-degeneracy assumption. If you don't know what that is, don't worry about it too much. If you do know what it is, think about it and see how these degeneracy gets connected here. The non-degeneracy assumption that I'm going to make is the following. If I take the objective vector and perturb it by a small amount, so I take a very small delta 1 and add it to 13, which is the first component, and take a small delta 2 and add it to 23, then primal opt remain the same. Geometrically, what this means is that the corner is sitting, the optimum is at a corner, and the two corners meet at an oblique angle, and therefore if I move the vector slightly, that corner still remains optimum. Algebraically, it translates to something called non-degeneracy, which has relationships to basic variables being 0. The same assumption I'm going to make for the dual. I'm going to say that if I perturb the dual objective by a small amount, the dual optimum remains the same. Just like in the primal, I can think of moving my objective vector slightly, and that would mean that the point doesn't shift much. I'll do the same thing for the dual. But the nice thing now is shifting the objective in the dual is shifting the right-hand side vector in the primal. So I'm making a geometrical fact about the dual LP here. I'm saying that if I move its objective vector, nothing happens to the dual optimum solution. But that translates to changing the right-hand side vector on the primal. So I'm going to make this connection between primal and dual and try to say something about what happens to the primal using the fact that things don't happen in the dual. All right? Okay, so let's start asking this question. Suppose, so this is the first question that one can answer using duality ideas. So suppose 10 extra units of tops are available. How much should you pay? So when I solve this problem by Excel, and we'll come back to it, we'll show you in a moment how these things work. After answering this question, I'll go back to Excel. The optimum solution is 12 and 28, and the optimum solution here is 1 and 2. So now I want to ask myself, Suppose somebody gave me 10 extra units of hops. So this is the hops constraint. How much should I be willing to pay for it? So I'm going to use this rule here, and I'm going to say, okay, so I'm going to pretend that I want to solve this LP. So I'm going to add 10 units here, and I'm going to say, all right, so suppose I were to solve that LP, what is the optimum value that I would get? One easy solution is resolve it. But sometimes resolving may not, you might want to just find out whether something is interesting or not, and using the dual you can. What happens is that changes the objective function in the dual. So this becomes plus 10 times the old U2 star. And now suppose the number 10 is small enough such that the dual doesn't change. So here's an assumption. Let's remove the constraints here. We know what complementary slackness is. So I'm going to write over here that suppose delta 2 equal to 10 is small. What is small? I don't know yet. That's the sensitivity analysis will tell me whether something is small or not. For now, let's just assume that it is small. If it is small, then my U1 star, my old optimum solution, remains still optimum. This implies that optimum dual solution is still equal to U1 star, U2 star equal to 1 and 2, which implies that the optimum dual value is going to be 480 times 1 plus 170 times 2, which is the difference would be 10. So it's going to be the old optimum was 480 times 1 plus 160 times 2 plus 40, right? No, 20. Therefore, the change, delta, so change in the objective, is going to be equal to 20, which means should be willing to pay up to 20. Right? So this whole idea, I mean, one of the reasons why we talk about the duals is basically to have this understanding. What happens to the objective when you change the right-hand side vectors? And the reason I could not have done it without looking at the dual is because when I change the right-hand side vectors, everything changes. The whole line moves up and down, so the solution changes. I cannot say, notice when I change this, I cannot say that the primal solution does not change. The primal solution will change. But what I can say is that the dual solution does not change because the objective vector there shifts, the constraint remains the same. And that allows me the ability to move over and answer questions regarding this. Okay, so what time do I have? Very good. Today Jenny has instructed me that I should get out on the dot. Okay, so let's go back to this. So here's what the Excel file is. And when you solve for it, and I did this in the morning to prevent myself this situation where I couldn't solve it here. When you ask the solver to give you an answer report, this is what it will give you. It will tell you the final objective value. It will tell you that the beer is going to be produced at 12 units, ale at 28, and this 2 and 3 was because I started out with a guess of 2 and 3. The cell value for corns and hops, both of them are binding. And then if you go to the sensitivity report, so we have just talked about this part here. We'll come to the story of reduced cost in a moment. So that also comes from duality. But here it tells you what the shadow price is, which is the optimum dual value. So there was a question at the beginning of class, what are shadow prices? The reason we call them shadow prices is because it gives me the value of the change in the objective. It's as if the constraints have a price. How much are you willing to pay for it? And that's why the dual variables are also called shadow prices. Now here we made an assumption that delta 2 equal to 10 is small. We can check whether that assumption is good or bad looking at this two columns. What is the allowable increase and allowable decrease? So delta there is an increase, so you can increase the value of delta by, you can go up to delta equal to 224 and still the dual variable remains the same. And therefore our assumption there that delta is small is valid. Okay? Same thing, for example, if the corns, I could allow the corn to increase by 120 units and still my optimum solution U star will still remain equal to 1. But one important thing when reading these sensitivity reports is that these things are only valid if you change only one of them. So when you're changing delta 2, you assume that delta 1 is 0. There is no change. If you change delta 1, then delta 2 must be 0. No change. In reality, you have a sensitivity in any possible direction. But Excel doesn't give you that answer. All right? Okay. So that's one type of question. And the next question that I want to answer using duality is this thing which is on a different sheet, if I can figure out where that sheet is, over here. So what's happened here is this is a new LP. What we did, and I want to, so let me erase this. Another kind of question that you can answer using duality is the following. Suppose this company decides to produce a new product. And that new product is, I don't know, light beer or something. It takes less amount of corn, so it's light beer. 10x3 plus it consumes 6 units of hop. And still you have the constraints of 480 and 160. And let's say they're pricing this product at 18 units. So this is not a dual for this right now. So let's just keep the dual here, but it's not a dual of this guy. Yes, question.
We know that we're willing to pay delta objective of 20.
Yes?
Is there possible that we know how much respectively x1 and x2 we respectively wish to change?
It's, well, okay. So the question was that if I know that I'm willing to pay 20 for the dual variable, then how would the x1 and x2 change? Well, looking at what happens to the objective, we can't say. But one thing you can say, which comes from this complementary slackness idea, which says that when you change it by 10 units, the dual variables still remain the same. If the solution is non-degenerate, which means that it's a very nice solution, for my purposes, non-degenerate is a fancy way of saying nice solution, then what happens is that you have this perfect complementary slackness. If the dual variable is positive, the corresponding constraints are tight, which means that if my dual variables remain positive, remain the same, I exactly know which constraints are tight. Now, if I know which constraints are tight, it's just a matter of solving a linear equation. So I know what the optimum solution is going to be. All right? Okay. So let's return back to this story now. So I know that the old solution was here, 12 and 28. And now what has happened is that this company introduced a new product. It wants to ask itself that suppose I start producing X3. Is it profitable for me to produce X3? Again, one possible solution is to just solve this new LP. And when I solve the new LP, it turns out the optimum solution for X3 is 0. You don't produce X3. Now what I want to think about is, could we have just looked at the primal dual solution that we had in the beginning and without even solving this LP claim, yes, you would not produce X3? How would we go about doing it? Any ideas? Just using, so X3 is a new variable that came into the picture. You have solved the old LP, which is sitting at 12 and 28. You've solved the new optimal solution, which is, or sorry, the old dual solution, which is 1 and 2. And then we want to say that X3 will be 0. How would one go about making that assessment?
It adds a constraint that 18 U1 and 10 U2
And 6u2 is less than equal to 18.
Greater than equal to 18.
Equal to 18. Which means it would be a slack constraint, and hence it would be zero
Variable. Good. One way of answering this question is, so there are two interpretations possible. One is the interpretation that the gentleman just gave, which is, if I construct its dual, then I would end up getting an extra constraint which would be 10 times u1 plus 6 times u2 must be greater than equal to 18. So when I put in a new variable in the primal, notice that the number of variables in the dual does not change. It's the same because the variables in the dual correspond to constraints. So changing something in the primal, adding a new variable just puts a new constraint. The old solution, which is 1 and 2, gives me 10 times u1 star plus 6 times u2 star is equal to 22, which is greater than 18. So the old dual solution is feasible for the new dual. Whatever was the old dual solution, it still is feasible. By adding a constraint, you can only make things smaller. And if it doesn't cut off that dual solution, then that must still remain optimum. And if that is still optimum, and this is slack, complementary slackness tells me that x1 star, x3 star must be equal to 0. Its corresponding primal variable must be 0. Okay? That's an algebraic way of doing the thing. A sort of a more intuitive way of looking at the same thing, which will give me the same exact answer, is the following. Yes, question.
What if it was 18? What could we do then?
What would?
If 10u1 plus 6u2 would be 18.
This was exactly 18, I could still say it's fine. I don't have to worry about it. And I'll tell you in a moment why this is true. But if this was 17, then I could conclude that this dual is no longer optimum.
So you have to solve again.
You have to solve again. Now, if you have to solve again, would you like to solve the dual or would you like to solve the primal?
The dual is easier to solve because the number of variables are lesser.
But you have infeasible solution. So you've got, so it's not quite the same in this particular case. The question that I was asking was that suppose this was 17 instead of 18, and the only thing I had with me is simplex. That's all I can solve with. Then what does simplex like? Simplex likes feasible solution, corners. The old solution, x1 star equal to 12, x2 star equal to 28, and x3 star equal to 0, is primal feasible. It's not optimum, but it's primal feasible. So I can move from there to a next corner easily. But in the dual, this variable is not even feasible. I have to somehow create a feasible solution. Constructing feasible solutions is bad. Don't like to do that. So if it turns out that something is bad here, so the rule of thumb is that if you're trying to solve an LP by introducing variables, typically very easy. Because the old solution is going to be feasible. You just have to move from there to an optimum solution. If you put in constraints, that's bad. Because the old guy goes away, he's no longer feasible. All right, so let's return back to this story. Another interpretation of the same thing is going to be, it gives you the same idea, but it just gives you a sort of a more economic feel for it, which is the following. That pretend that we produce delta units of x3. So let's say, this is sort of like we're doing simplex. We're really saying that we are sitting at this optimum solution, and we're saying that x3, which is currently a non-basic variable, it's set equal to 0. Let's start producing it. So when I produce delta units of x3, then what happens? So I have this much, 480 minus 10 delta and 160 minus 6 delta available for x1 and x2. If I produce a small amount of x3, then it will use up my resources. Every unit of x3 uses up 10 units of corn and 6 units of hops. So delta would use up 10 units of corn, 10 delta, and 6 delta units of hops. Okay. Now what I will pretend is that now I'm going to solve an LP with this right-hand side vector. Once I have produced delta units of x3, this whole thing is gone. It's no longer there in my LP. This is gone. So I still have my old LP. The old LP that I did solve with the same with the right-hand side vectors changed to this. So the change in the objective will be equal to the change, which is minus 10 delta times u star 1 plus minus 6 delta times u star 2. Right? This is how the objective will change because the right-hand sides have changed. The Korn right-hand side changes by minus 10 delta, so I multiply it by its dual vector. The Hop's right-hand side would change by minus 6 delta, so I change its right-hand side vector multiplied by its dual variable. So this will turn out to be minus 22 delta. And the revenue that I get is equal to 18 times delta. So this implies a net loss of 4 delta, no production. Yes.
I don't understand why can we disregard the 18x3 in the max function, because the max function indeed changes the new problem.
Okay, so the question is why do I disregard 18x3? Well, you can think of it in two different ways. If you want to think about the fact that the primal has changed, then take this interpretation. In this interpretation, the 18 has not been forgotten. It's sitting here. If you take this kind of interpretation, then what I'm saying is I've produced delta units of x3. The contribution that I get from this part is gone. It's fixed, 18 delta. So all that is left over is how do I produce x1 and x2, right? And then where that 18 delta comes back is here. So once I decide to produce x3, its objective has no meaning. It's just a constant. It's just sitting there. I produce x1 and x2 using this. I get a minus 22 delta. I get a revenue of 18 delta because I produced x3 at delta. Look at the difference. You get a loss of 4 delta, so no production. So what does it tell you? What is the minimum price at which you're going to produce? 22 delta. The minimum price at which you're going to produce this product is 22. Now if you went and so that's one way of getting this thing by duality. If you go back and look at its sensitivity report of this one, you end up getting that its reduced cost is minus 4, which is exactly that loss of 4 delta. So when you talk about changes in products, when you add products and you want to find out when something is going to be basic, meaning that you would actually produce that, you look at the reduced cost. If reduced cost is 0, it means that is sitting in the optimum solution. The final value is 12 and 28. It's a positive value. If the reduced cost is negative, it means that it will not sit in the optimum solution. You're making a net loss using that variable. You will not sit in the objective. And the amount by which you're making a loss is the value of the reduced cost, minus 4. You can get the same result by looking at basically the dual variables. So the information that's sitting up here can be constructed using the dual variables, but it's conveniently there. So if you want to use that, you can look at it. But in order to get that reduced cost value, you had to formulate an LP. You had to formulate this LP, which already had the third variable. Whereas this sensitivity report, which did not have the third variable, had the information available for you to decide whether that third variable is going to be positive or not. Okay? All right.
Then if we could go to the sensitivity report too.
Yeah?
Here, the allowable increase is only 4, as in you can only increase it by 4. That would be it. So after that, you wouldn't increase the price for the third product anymore.
No. What it means, okay. So all of these so the question is, what does this allowable increase mean? The allowable increase and allowable decrease basically refers to the fact, how can I change my objective coefficient without ruining my current solution? What this tells you is that if you increase the objective value of this guy by more than 4 units, this solution that you have created is no longer optimal. Which makes sense. If the price is more than 22, then you will produce x3, which means that x3 equal to 0, which is sitting here, is no longer an optimum solution. So this allowable decrease and increase doesn't mean that you cannot increase the product's price by that amount. The only thing it means is that if you move it by more than that amount, this solution is meaningless.
You need to resolve.
You have to resolve. Okay? So duality and sensitivity analysis can only work for a small interval. If things perturbs by a small amount, it works. If you perturb it by too much, it doesn't work. But it has a nice way of interpreting what is the price that you pay for a particular constraint. Okay. Good. We still have time. Good. So we learned about, this particular result that's up there, which says P is equal to D, in the literature it's called strong duality. Strong duality, this means weak duality, meaning that dual is an upper bound on the primal. That is strong duality, which means that if primal and the dual are finite, then they're equal. It's a stronger version of this statement. Complementary slackness allows me to make statements like this. If I want to look at it from the perspective of hypothetically constructing the dual and seeing whether I would produce x3, the dual variable is dual constraint is slack, so its corresponding variable, which must be x3, must be 0, which is what complementary slackness tells me. So this algebraic property of complementary slackness helps us decide things of that sort. And the other thing is the dual variables. I don't like the word shadow prices. I'd rather call them our constraint prices. So they tell you what is the value of a constraint. How much should you be willing to pay to change a particular constraint? Or what is the cost of the constraint being changed on you? Suppose a supplier tells you that only 470 units of corn is available. Then you want to figure out what is the implication of that for your production. Dual variables tells you that. And all of this analysis is local. Meaning small changes are okay. Big changes, can't say. You cannot say anything about it. The optimum solution could move anywhere. But if it's small, the dual variables tell you what happens. Right? So let's do one more exercise, since I don't have the time to go into the other thing. Let's just try one more exercise and see how this works out. Just on using duals. Suppose the profit from ale drops to 20. Would X star equals to 1228 remain optimum? So what has happened here is, let's go back to so we don't have x3 here. Oh, well, let's keep it here, doesn't matter. What has happened here is that the profit from ale, which was originally at 23, suppose now it drops to 20. You re-estimated the profit that you could get possibly from ale, and it's now to 20. And now the question is, whether this solution, 12, 28, and since I'm looking at a different formulation over there, let's put a 0 there for x3. Is this solution optimal? Yes. How did you decide that this is optimal? Allowable decrease here is 3.2. Sorry, no, 10. 23 changed. So the allowable decrease is 10 units. So as long as my decrease is within 10 units, and the decrease here is of 3 units, old optimum solution remains optimum, and therefore I'll still produce at that level. Now, the other thing that's a simple use of sensitivity. And in the afternoon, we're going to look at various modeling questions and look at different interpretations of the same ideas of sensitivity. I mean, the same ideas of dual variables will show up in different ways. But before I close, I want to talk about one more thing, and then we'll quit, which is an intuitive thing, but there's always there is diminishing. So outside the small range, outside the range, you can predict something by diminishing returns or decreasing returns or whatever you want to call it. So to give an example of that, let's say that it's allowed to increase by 120. So let's say that the Korn constraint which was sitting at 480 now goes to 650, suppose. What is the change in objective value? So I'm allowed to increase the right-hand side, 480, by 120 units. So I can go up to 600. And up to that point, I'm guaranteed that my dual variables are the same, and therefore I know that the change will be 120 times 1, 120. This guy, 650, the difference between that and this is what? 170. That's outside that range. So what can I say? Is there some way I can find out what will be the change? Bounds on the change? I can't say for sure. To say for sure, I'll have to solve the dual again. Solve the primal again.
So would you also need to look at whether this is binding or not?
Yeah. All of those things have to happen. I have to resolve. Outside that range, I don't know. But I can still tell you some bounds. Yes?
What if we say that, if we solve the dual and say that the change would be 120, and then we'll have a bound. 120, we can change 120.
Yes, 120 will be a lower bound or an upper bound?
A lower bound.
Lower bound, good. So the lower bound on this value would clearly be 120. What about an upper bound? Can you give me an upper bound? So that's what it turns out is that we haven't talked about this property of convexity. It turns out that if you change the right-hand side, so here is 480, within up to 600 and whatever is the decrease, 280, in the region 200 to 600, this looks like a straight line of slope 1. Right? Slope equal to 1. So if I change my constraint in this region, I know that the value, and on the y-axis here I'm plotting the objective value. That's what the change in the objective value looks like. It's a straight line with a slope equal to 1 because the dual variable is 1. It turns out that the function is going to be concave outside this region. So it's going to drop and become steeper here. That's what the shape looks like. And you can prove this. And we'll come to it when we talk about nonlinear programming. Here I just want to give you a feel that you can get bounds. So when it flops up this way, it means that the two places it can be is this straight line, which is perpendicular to the axis, and this line continuing forward. It can be anywhere in that region. So as was pointed out, if it becomes flat, then you get the change to be 120, which is a lower bound. If it continues growing up in the same way, and it can, because all that the range says is that this particular dual vector cannot be optimum. But it is possible that outside the range, this still remains 1, but that guy changes to something else. So that still remains 1, so you get an upper bound which is whatever, 170 times 1, which is 170. So you get a lower bound of 120 by looking at that the slope drops to 0, and you get an upper bound by saying it continues forward by the rate 1. And that comes by looking at certain other properties of primals and duals, by looking at what happens to their structure as nonlinear programs, but we haven't talked about nonlinear programs right now, so when we talk about them, we'll return back to this example and make it concrete. All right, so let's quit at this point. And although the notice has gone off the board, you remember that you have to be here if you want a job.